Hello everyone. In this video we're going to be solving a logarithmic equation with natural log. We have ln x plus y plus 1 equals ln x plus ln y. You could also change this equation a little bit by adding a 1 to the right hand side. That was my original plan, but then I thought about it. This is a nicer version. So how do we solve such an equation, right? We have the sum of two ln's on the right hand side. So I'm going to go ahead and combine them using properties. Properties of logs, I'm thinking about making a video on properties of logarithms. I don't know when I'm going to be able to put it together. Lecture videos take a little while to prepare, but anyways, I'm thinking about it. So, but let me just tell you, if you have ln x plus ln y, you can write it as ln x times y. So that's a really nice property. So let's write the right-hand side as ln xy. We can't write the log of a sum. We can't break it down, but if you have a product or a quotient, you can always break it down. So the expression on the left-hand side is kind of unbreakable. That's why we had to work on the right-hand side. Make sense? But now we have the ln's on both sides. If ln's of two things are equal, then they are equal, because ln is a one-to-one function. If you look at the graph, if you differentiate it, so on and so forth, and it's only defined for real numbers for positive x and y values in this case. All right. So let's go ahead and set these equal to each other. And I would like to take the xy first. Set it equal to x plus y plus 1. And like in the previous video, I'm going to be using Simon again, because Simon is calling. Let's see. I'm going to put x and y on the left-hand side. And then factor out x. And factor out -1. Now, notice that I do need a y minus 1, but there's a -1 on the outside. That's going to multiply the -1, which is going to make it positive 1. So I'm subtracting 1, but I'm actually adding 1 to both sides. Make sense? I hope it does. If you distribute, you're going to notice that we're actually adding 1, not subtracting 1. Okay, so now it's factorable, thanks to Simon. X minus 1 times y minus 1 is equal to 2. Awesome. I forgot to tell you what kind of solutions we're looking at, right? Well, some people are thinking, okay, are we going to look for integers? Are we going to look for reals? Are we going to look for rationals? First of all, we're going to look for the integer solutions, and then I'll show you the real deal. Okay, so in this case, we have a Diophantine equation, and to solve this, we just have to look at the factors of 2, and there aren't that many, right? For example, if x minus 1 is equal to 2, that means y minus 1 is equal to 1. So from here, x equals 3 and y equals 2. That kind of gives us the order pair 3, 2. But notice that our equation is symmetrical, right? So if 3, 2 is a solution, 2, 3 will also be a solution. So we don't really need to check that. Okay, good. Let's go ahead and look at another scenario. How about x minus 1 is equal to 1 and y minus 1 is equal to 2? This implies, well, I just can contradict myself. We don't need to check that. Okay, I meant to say, what about x minus 1 is -2 and y minus 1 is -1? Okay, cool. In this case, I get x equals -1 and y equals 0. Now, this is not good, even though you might be thinking, hey, -1, 0 is a valid solution, or 0, -1. This is problematic because our ln function, the natural log natural, right, the French method, is not defined for negatives and 0. It's only defined for positive values. Therefore, we're going to reject these values, and we end up with 2 ordered pairs for integer solutions. Now, do you want to see the real deal? Let's go ahead and take a look at it. So for my real values, I'm going to write this equation a little differently. So let me rewrite the original one after the condensation of the logs, right? Is that the right word? So let's go ahead and put the x, y, and y together. I hope you know why we're doing this. And then we're going to take out the y and solve for y. Yay. From here, we get y equals x plus 1 over x minus 1. We could manipulate this a little bit. So let's go ahead and do that. And I'll, graph this. I graphed it for you, so I'm going to show you the graph at the end as well. And we'll talk a little bit about this function. So this is a rational function, and it can be written as x minus 1. So I want to make the numerator look like the denominator. So I write it as x minus 1, but I have x plus 1 in the numerator. So why not add a 2 to balance it out? Okay, cool. This works. This is a really nice strategy. Now I can separate these and write it as 1 plus 2 over x minus 1. So it's kind of like adding, not adding, unadding two fractions with the same denominator. Okay, we're kind of separating them. So this is really cool because now you can kind of look at the pieces that make this function important. For example, it has an x, what is it called? Not x. It's called a, okay, vertical asymptote, right? It has a vertical asymptote at x equals 1 because if x approaches 1 from the right and from the left, the limit approaches infinity. Some people say does not exist, but you know, that's what happens. And it also has a horizontal asymptote because if x approaches infinity, did I say x approaches 1 from the right? Yes. Okay. If x approaches infinity, this becomes super duper small and y approaches 1. So y equals 1 is a horizontal asymptote and x equals 1 is a vertical asymptote. Our graph is going to be between those lines that intersect at 90 degrees. Let's go ahead and take a look at the graph, and then I will tell you. So what are the solutions? You can write the solutions as x comma 1 plus 2 over x minus 1. So basically, if you can replace x with certain values, such as, for example, well, obviously you don't want x equals 1 in this case, right? Because there's an asymptote, so x cannot equal 1. But let's say x equals 5, then you're going to get 2 over 4, which is 1/2. That's going to be 3/2. So you're going to get 5,3/2 as a solution to this equation. There's infinitely many solutions in this case because you can replace pretty much x with anything except for 1. And that also means that y is never going to be 1 either because that's an asymptote. Okay, anyways, let's go ahead and take a look at the graph and kind of wrap it up. In this graph, we have a rational function, and as you can see, it has 2 dots that I marked on this, which is 2, 3 and -1, 0. Well, what do those points represent? Those points basically represent the solutions, the integer solutions to this equation. So if you're looking for integer solutions, those are the integer solutions. But remember, our original equation had a natural log, which does not accept negative solutions. So unfortunately, we're not going to be able to accept this solution. But if this was a different equation without the logs, then obviously -1, 0 would work in this case. And if you're looking for real solutions, then every point on this graph is going to be a solution. And you don't see that necessarily because I forgot to graph them, but x equals 1 here and y equals 1 here are asymptotes, right? So basically the graph is not gonna cross it. All right, if you want to know, sometimes graphs can cross the horizontal asymptotes. They can never cross the vertical asymptotes, but horizontal asymptotes can sometimes be crossed. And to find out if the horizontal asymptote can be crossed, you can basically set the y value equal to 1, and from here you're not going to get any solutions, which means our horizontal asymptote in this case will not be intersected because 1 never equals -1, right? Hopefully. All right, and this brings us to the end of this video. Well, thank you for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you tomorrow with another video. Until then, be safe, take care, and bye-bye.